doubt in previous class.
Yeah, I'll explain that. So what we learned in the last few classes, last class, what we learned is one, a column takes compressive axial load, right? And moment, which we'll see today. Two, a column can fail in strength, in which case column bending moment is greater than sigma level, right? Or in stability, we call it buckling. When PCR, sorry, when P is greater than PCR, right? When P is greater than PCR. This is generally for short columns, and this is generally for long columns. What is a short column? A short column, when you have L by R, around 30, 35, right? Okay. And long columns, when your L by R ratio is greater than 80 to 85. All right. In between this is called intermediate column.
Hello, sir.
Yes.
Sir, R depends on capital I, right?
R depends on?
I. Moment, second
Yes,
moment of question.
R is square root of I by A.
I by A. So with cross section means with this x distance along the column, I might change, right?
Yes, it might change, of course.
So how can it be L by R for a whole column? Since we
No,
can't
you
write
have
a
to,
single L, right?
no, you have to take, the ratio L by R where it is max. So work with minimum R. That means when you have I minimum, because I minimum will give you less resistance. So that is the portion where the failure can be more. Right? So work with minimum R. So minimum R will give you maximum L by R, right? And your maximum L by R should be this rho Jones. So, and these values, 30 to 35, 80 to 85 are not, written in Bible. So they are not fixed values. You have to analyze your column. The rough idea is if your L by R is greater than 80, 85, then for sure it's going to fail by buckling. Okay, for sure. But it doesn't mean that you will not check in strength. You have to check in strength, but your design can start from buckling idea, buckling direction. For short columns which are lesser than 30 or 35, I should not write equal, almost equal to, I should write lesser. Okay, 30, 35. In that case, your design should start from strength point of view, because the failure can happen in strength. Then you check for buckling. Otherwise, if you start from buckling point of view, you get a load, you check in strength, you say that it's not getting into strength, your strength is failing, then you revise your design. So you have to do double design, right? The idea here is this give you some direction of starting the design. So these values are not concrete, they are not fixed values. They can vary with material, right? They will vary, definitely they will vary with material. And therefore you have to be careful with it. So you take these values with a pinch of salt. That these are rough ideas, that if your L by R ratio is greater than 80 or 85, you start your design from buckling point of view. So you get your force first from buckling, and then you check for strength, and definitely it will be lesser in strength. If your L by R ratio is around 30, 35 or lesser than that, we call them short columns. Then you start your design from strength point of view. So you check your load P based on what is the maximum strength the beam can go, and then check that load for buckling. Okay, so in that way you don't have to do double design. You will be safe in the first design itself. So that's the idea of writing this. All right, and then we saw that the column is defined by a formula. This is for ideal columns. Okay, load is along the central axis. In that case, I get a formula which is EI or Y, right? We wrote Y double dash plus it was P into Y is equal to 0, right? Plus two boundary conditions. This is the second order differential equation with a constant coefficient P and EI, and it's a homogeneous one, right? It's not with a forcing function. It's a homogeneous one. Now, if it's a homogeneous one, we got its solution Y to be A sine n pi x by L, right? For simple supported columns. Okay, and we saw into leads to eigenvalues and eigenvectors, or we don't write vectors, eigenfunctions, because you get a sine function here, you don't get a vector, right? And eigenvalues gives us the critical load for buckling, PCR, which is pi square n square pi square EI by LE square, right? N square pi square EI by L square for, and we saw that LE is equal to L for simple supported columns, and LE is equal to 2L for cantilever. LE is equal to 0.5L for fixed, and so on and so forth. LE is equal to 0.7L for propped, right? This is what you saw, and you had few questions in this, right? So we'll go back to these questions now, and we have to do one problem where we understand how to design columns. Okay, and then we'll go what happens when you deviate from ideal columns, when you deviate from ideal columns and go to columns where the load is not along the central axis. Okay, right. So what were your questions? Where should I go? I should go to this point. Yeah, you had some questions. Can you tell me what were the questions?
No, sir, above.
Huh?
Above.
Hello? Above, okay. Here.
Yes, sir, yes, sir. Sir, two questions.
Yes.
First, this MB. Means this got
Yes.
cleared yesterday night only. The second equation, MB equals to minus P theta L by 2. We have assumed it to be small theta, right?
Yes.
Okay. Okay, then. The first question got cleared last night.
Yeah, so this is actually the spring force, right? Spring moment that the rotational spring is resisting, and that is given by VR into theta. Now the spring has moved not only by theta, it has moved by 2 theta, right? If you take it like this. No, if you take it from here, okay. So this is your theta. And here also there is theta. So there are two theta movement. And this two theta movement is what is coming here for 2. Okay, and you're resisting from one side, it is L by 2. From two sides, it will be 2L by 2. So therefore, so this length is L by 2. Okay, so if you have no questions here, we'll move on. We'll solve one problem in columns, so that design of columns will be clear with that. Okay, this.
Hello, sir.
Yes.
Sir, we have the small r is equal to under root of I by a, right? Sir, for divergent columns, like for area is increasing along the axis, which area we have to consider, sir, for that? For
Generally, column in
like, sir,
column
in
design,
yesterday in
yeah,
class, sir, there is a water tank stand on the one column which has a
right.
diverging, which is for stability. So it has a at the top of it, it has a small area, and a bottom it has a
Right.
large area. So which area we have to consider for that?
So you have to consider the area which gives you lesser load. Now you check from the backside, which one will give you lesser load. So your PCR is pi square EI by L square, right? Your L is constant, pi is constant, E is constant. So your PCR mean is going to be equal to pi square EI mean, right? By LE square. Okay.
Yes, sir.
You'll get another PCR, which will be PCR max, which will be pi square EI max by LE square. Now, let's say that I consider this one, pi square EI max. Now, if I consider pi square EI max, I get a PCR max, but the section that has this I will not, cannot take up that load, right? It will fail, isn't it?
Yes, sir.
Right? So I cannot give this load there. I have to choose PCR mean, because in that case, this smaller section with smaller I will take up that load. Even the higher section can take up that load, right? So I am safe. My design is always a safe design. I have to always go for a safe design. Therefore, I have to choose this one and not this one. Okay.
Okay, sir. Means sir, we have to take a minimum area, right?
Yeah, wherever your I is minimum.
Sir, when we calculate the I, we calculate the for whole column, right? Like we
No,
integrate a
I
y
is
square into dA from whole
over a
column.
section, not over the length.
Okay, sir. Got it.
Right? I
Yeah.
is always calculated over a section, not over a length. So every section
So
can
yeah.
have different I, as you said.
Yes, sir. Now
It
I
may
got
not
it. Yes,
have minimum area, but it can have minimum I. Hollow sections, the column that we are talking about, they will be mostly hollow. And if it is hollow, some portion will be solid, some portion will be hollow. You have to always calculate I.
yes,
So it
sir.
is based on I, not based on area.
Yes, sir. Got it. Yeah. Thank you, sir.
Okay, so let's go into a problem. Where is the problem? Yeah, here. What the problem says is we have a 2-meter long pin-ended column. When I say pin-ended column, this is the pin, okay? So this is 2-meter long. And its cross section is a square. So this is the cross section. Okay, section AA or whatever you want to name it, you can name it. And it is made up of wood. You assume that its modulus of elasticity is 13 GPa and its allowable sigma is 12 MPa. Using a factor of safety of 2.5, so there is a factor of safety that is given of 2.5 in computing the Euler critical load for buckling. Determine the size of the cross section. So I have to design A, right? So this is a design problem. Of the column is to safely support, okay, safely support what load? Safely support 100 kilonewton of load or a 200 kilonewton of load. So I have been given two different loads. One is 100 kilonewton. We'll first check what happens when you have 100 kilonewton load, and then we'll also check what happens when you have 200 kilonewton load. Okay. So what are the things that are given to me? P is given 100 kilonewton, length is given, E is given, and sigma allowable is given, right? And also a factor of safety is given. So factor of safety means whatever is the critical oil buckling load, you have to divide that by 2.5, and that will be your design load, right? So your design load going to be different from your capacity of carrying that load. So now, first let us check with the design, start design from buckling point, because it has already said critical load for buckling. Let's start from there. So critical load for buckling is going to be, first mode is going to be the more critical, right? We cannot go to second mode unless there is a support here to go to second mode directly. So you have to do it for first mode. So if I do it for first mode, it is pi square EI by LE square. Pi is known, E is known, I is not known, LE is known, right? And factor of safety is 2.5. So your PCR by P is going to be, should be greater than 2.5 for the cross-sectional design. And this is not, we can write it for better thing, that is, this is P design. Okay, P design. And then you can do the calculation. If you do the calculations like you 2.5 into P design is going to be 100 is given, right? So this is my design load. It should carry 100 kilonewton. That means this is my design load. So its critical load going to be 2.5 times this, because factor of safety is 2.5, right? So that comes out to be this. Now, which will tell you, all the values are known except for I. So that gives me I as this, right? And if you calculate, you get I as this. What you have to do now, you have to calculate for a square cross section, it is told. So if it is a square cross section, I can write I is equal to A4 by 12, and then I can calculate for A, which comes out to be 98.3. So I cannot take any value of cross section which is lesser than 98.3, but I can always consider greater value, right? Higher value will give me less stress, and it is also bigger area, so it will have bigger I. So therefore, its requirement of PCR will be higher in that case, right? So a higher value of cross section is better, so I'll go for higher value of cross section instead of 98. You cannot design 98.3 exactly, but 100 mm can be designed. So I'm taking 100 mm by 100 mm as my cross sectional area for the first load. Now this is not enough, right? I have to check whether the column is going to fail in strength or not. So check for strength. So what is going to be sigma? Sigma is going to be P by A, right? It's an axial member, so it's load by area. So now load, it's 100 into 10 to the power of 3, and then you do all the calculations. So, and this has to be converted to meters, so 10 to the power 6 on the top. So it calculates to be 10 into 10 to the power of 6, which is lesser than design sigma. My design sigma is 12. That is what given to me, right? Sigma design is 12, allowable. So that is going to be 12. So my design sigma is is greater than my sigma. So let's not write it as design here. Let's write it as allowable. Okay, and then let's also do it this way. Let's say this is my design sigma, because I am writing PD. Sigma D is lesser than sigma allowable. Okay, so design is safe in strength. So my design is okay. So for a load of 100 kilonewton, I can use a cross-sectional area of 100 mm by 100 mm, and I can be safe from buckling point of view, as well as I'll be safe from strength point of view. But this design started from buckling style, right? Now let's look at for 200 kilonewton what happens. So now I have 200 kilonewton as my load. Okay, so let's check PCR. I start from again as before. I take first load as pi square EI by LE square, and I do all the things P design. Let's write it again as P design, and I get some value here, and then I take A. Same thing I do, and I get 120 mm, right? So my design is like this: 120 mm, 120 mm. Now let's check in strength. Oh, I've already drawn that here. Sorry, it's already drawn here. So now check strength. So in strength, if I check sigma design, comes out to be P design by A, and then you do the calculation, you get 13.89, which is greater than which is greater than sigma allowable, right? So this is my allowable sigma, which is greater than my sigma allowable. So therefore the design will fail in strength, the concrete will fail, or the column will fail in strength because it is going beyond my given capacity allowable, right? So what I have to do? I have to revert back to my design from the strength point of view. So restart the design from the strength point of view. So area is going to be PD by sigma D, right? AD is going to be PD by sigma allowable. And that if you calculate, so PD is 200, that is given to me, and my maximum strength, allowable strength, is given to 12 MPa. So you can do the calculation. You have to convert everything into same unit, right? So don't worry, don't make a mistake there. So here sigma D is equal to sigma allowable. Okay, so if I do that, I get 16 meter square as an area. So you can calculate your side. Each side is going to be 129. You cannot take 129, so we'll take a higher length, so higher width. So we go to 130 mm, right? Now check for buckling, whether it's safe in buckling or not, because we have to check for both. So we come here, PCR pi square EI by LE square, where pi is given known, E is known, I will be based on this, right? So I calculate I here, and then LE is 2 meters, so 2 square. Do all the calculation, you get 762.67 kilonewton is your PCR. Now, what is the factor of safety? Factor of safety is going to be PCR by whatever P you have designed for, right? So it's 200, 762, which is 3.81 and greater than whatever is minimum factor of safety that is given to you. Therefore, it is safe in buckling too. Therefore, 130 mm square is the design cross section of the column, right? So this design actually tells you two things. One is if you start design from buckling, you have to check in strength. If it fails in strength, you have to go back and do it again and check for buckling. Okay, so what is PCR and PD? Now PCR is the max load that the column can carry, right? Okay, but I cannot give this always because there can be a lot of uncertainty. There can be various uncertainty in the structure, right? So I as a design engineer can tell you that, design it for 700. For example, here it has come to 700, right? Design it for 700 kilonewton, and I get a cross sectional area and I do everything. But as an engineer, I'm not going to build it on the field, right? In the field, it will be built up by the masons, or engineering site engineer will support it. Now, while the mason builds it, or the contracting workers who builds it, they cannot do it as an ideal when I do an analysis. When I do an analysis, I am assuming the structure to be homogeneous. I am assuming that the areas are completely constant all through, right? When the design is made, when the column is built up, everything is perfect. But even if it's perfect when it's built up, after a certain time, it can start getting withered because of weather conditions. There can be a lot of other things that can make small cracks to develop, so it will lose in strength. In those cases, if I have put the design strength to be equal to PCR, then it will start failing because it will not take. That's why you need to bring in a factor of safety for all those things. And that factor of safety here is told as 2.5. So whatever load is your PCR gives, your P design should be equal to PCR by 2.5. So you are reducing your design load. The structure should not carry more than your P design load. That's why even if there is an error in calculation in design load, if there is an error in building up the structure column. If there is a wither or there is a small cracks that have developed, you will still be safe because your design load is much lower than the strength, that maximum strength that it has. Clear? I hope that's clear.
So
Yeah.
So does that mean if PCR is high, then there will be like more factor? Okay, that's so like
PCR is
safe.
high.
So if PCR is high, then we can have a, what to say? Okay, sorry, I understood.
More safety.
Yeah, yes.
Yeah. Now we will look into columns that do not carry load axially. Okay, we call it eccentric column. Right? What is it? It tells that if I have a column, let's say I have a column here. It's mostly used in gantry girders. Let's say I have a column here, and the load is somewhere here. Okay, and you have a gusset plate or some plate to hold that load and bring it to the column. So in that case, the column will not have only a load, it will have a load and a moment, which will be P into E. This is a load P, right? And let's say this is load eccentricity E. Okay, so E is distance between the column axis and the position of the load. M0 is equal to P into E, is the moment that the column needs to resist due to eccentric load. Okay, so now you assume that your structure has bent. Okay, now if it has bent, it will carry some bending moment. It is carrying some bending moment. It will also now carry a bending moment because of its bending, like we did in the last part of the last class, right? So let's say my structure is like this, and with a load here P. Okay, so when it bends, let's say this is my Y. Okay, and there is this load that is here. Let me draw it straight, otherwise it will become non-linear. So let me draw it straight here. So if I take a section out of it, it's going to look like this. This is my Y, and there is going to be some moment it has to resist, that is M, and it has to resist a P force, right? My free body diagram. That is how it is going to look like. And there is a P force here, which is at a distance of E. So I can write this expression in equation as M is equal to P into Y, right, plus E. Minus. Is that okay? So my moment is in anti-clockwise direction. So that's positive, and this force is also giving an anti-clockwise. So m plus p into ye. Okay, let's write it that way. M plus p into y plus e is equal to 0. Summation of n equal to 0 at cross section. So that gives me m is equal to minus p into y plus. And we know our equation is ei d square y by dx square is equal to m, and that's going to be equal to minus p in terms of the load plus e. So now let's go ahead and solve this. Plus, let's go ahead and solve this problem. Ei y double dash plus p into y is equal to p into eccentricity. Okay, plus boundary conditions has to come.
So minus of p into s.
Minus of
Minus p because RHS.
yeah, minus p. Yeah, then
So last line that you wrote.
yeah, I wrote
Instead
minus
of p,
minus of p into y plus e.
last line of the next page.
This line. Okay. Yeah, sorry.
Sir,
Yes.
so I have a doubt in the previous slide, sir.
Okay.
We wrote moment at some x no, sir, from the top.
Yes.
In that, actually, shouldn't we first write the force? I mean, the force is on the rod due to the fixed surface, and then shouldn't we write the moment and shear force equation rather than just considering only the external force which is acting?
Meaning?
No, so like what I'm trying to say is, because of this force P, sir, which is acting externally, the fixed surface will produce a force P and MP, so moment, like which we wrote in the previous.
Yeah, so that if I convert this load, if I take this load to this point, I'm not taking it, right? It is same. It is same as writing this. Here there is a load P and a moment m0 equal to P into E. It's same as writing that.
Okay.
Which color do I use? Right. So then in this point also you will have P and a moment m0 equal to P into E, right? But now the distance is only going to be Y. Right?
Yes, sir.
Clear? So
Yes, sir.
it's going to be the same thing. Okay, now if we have this, now it's no more a homogeneous equation. It's a inhomogeneous equation with a constant at the right hand side, right? So the solution for this, what will be its particular integral? Homogeneous solution, we know it's going to be sine into and cos, but what about its particular integral? Consider a simple support case. What will have? Y at 0 equal to 0, y at L equal to 0, right? That is what we are going to have for a simple support case, the boundary conditions. These are my boundary conditions. All right. Now, I know the solution is going to be y of x is going to look like C1 sine. Let's write something here. We can write it as P by EI is equal to lambda square again. So lambda. So let's write that equation in a different format. Let's write this equation into, instead of EI, I'll write it as y double dot plus P by EI y is equal to minus p by ei into e. Okay, so it comes out to be y double dash plus lambda square y is equal to minus lambda square e. Lambda square equal to p by ei. So that gives me the solution to be y of x is equal to c1 sine lambda x, right, plus c2 cos lambda x plus what will be the particular integral? The particular integral is going to be, you see, how do you choose particular integral? Anyone? How do you choose
Right
particular
answer is
integral?
just a constant, sir. So right answer is just a constant of degree 0. So it will be just a constant.
It will be just a constant. What will be that constant?
Minus c.
Minus e. Very good. So we will assume that this fellow is not there because we are looking at a steady state solution. So this fellow, we will assume that there is no dynamics, there is no motion into it. So this fellow is not there. Therefore, y is going to be lambda, lambda cancels, minus e or plus e, whatever you want to consider, you can consider. Okay. So let's write. Okay. Now, whether you consider minus or plus doesn't matter because the sign will C1 and C2 will come accordingly. If you choose minus or if you choose plus, it will come accordingly as you need to. Okay. So now we need to find C1 and C2 based on what we know the boundary condition C1 and C2 to be taken from the boundary conditions. And if you do that, but you get y equal to 0, y at 0 is equal to 0 gives me C1 into sine is 0, so C into 0 plus C2 into cos 0 is 1 minus E is equal to 0. So that gives me C2 equal to E, right? And y at L equal to 0 implies that C1 into sine lambda L plus C2 is E, right? So E into cos lambda L minus of E equal to 0, which implies me, so I can solve it and I can get C1, right? So that gives me C1 as how do I do it now? It will give me C1 as, yeah, equal to that E goes that side, E minus E cos lambda L by sine lambda L, right? Yeah, so this E goes this side becomes plus, this goes this side becomes minus, and that divided by this. Okay, I think I'm correct. Please check it yourself. Okay, and that I can write as E outside 1 minus cos lambda L can be written in terms of sine, right? 1 minus cos lambda L can be written as in terms of sine, right? So that becomes 2 into sine square lambda L divided by sine lambda L also can be written as 2 sine lambda L by 2 into cos lambda L by 2. There will be a 2 here, yeah. So now I can cancel each other and write C1 very, in a very nice way, that C1 is going to be equal to E tan lambda L by 2, right? Isn't it? So, these two cancel, square and sine cancel. So sine by cos is tan lambda L, right? It's correct. So C1, I can write it as this. And therefore, your Y now becomes equal to E tan lambda L by 2 into, what is this? Sine lambda L, right? Sine lambda x, not L, sine lambda x. And then plus E cos lambda x minus E. Is that correct? Yeah, that's correct. So I can take E out, and this can be written as tan okay, so that's going to be your deformation or buckling deformation when you have eccentric load. Okay, so this is what you have to remember, but there are a lot of things now to do. What are these things to be done? One is to check what will be the maximum deflection. Maximum deflection. What is going to be the maximum? How are we going to find maximum deflection? Maximum deflection is going to be when you have, this is a symmetric structure, right? Symmetric structure. So it's going to bend something like this. Right? So your maximum is going to be at Y max is going to be at L by 2. Right? So I can write that here. I can use that symmetry here with deflection maximum for SS column is at L by 2. So Y of L by 2 is going to be equal to, you put L by 2 everywhere. So sine lambda L by 2 cos lambda L by 2 minus 1 is going to be E into tan lambda L by 2 into sine lambda L by 2 in plus cos lambda L by 2 minus 1. So that will come out to be E into, what will happen? There will be sine into sine by cos. So it will be sine square lambda L by 2 by cos lambda L by 2 plus cos lambda L by 2 minus 1. If you add these two, this will become E into sec lambda L by 2 minus 1. Okay, so that's going to be your maximum deflection E into, let me write it in terms of P. So it is going to be root over of P by EI into L by 2. Okay, clear? So that's going to be your maximum deflection, and you have to then find what is your maximum. Okay, now this is your maximum deformation, right? Now, how do you find your PCR? From here, can we make E equal to 0 and find my PCR? Okay, that I'll give you that homework. Find the limiting case E tends to 0. Can we get back to Euler Backton load? Can we get Euler click load? Try it and see whether it happens or not. Then probably you have to find your maximum moment, right? And then we have to, so there are a lot of things you can do now. Maximum deflection, after getting maximum deflection, what will be the maximum moment at the center, bending moment with eccentricity, all these things you can find, right? I have to tell you a few discussions. I'll just take another 2-3 minutes. One is the point one is the force deformation relation is not linear. Okay, so superposition is not valid. Very important discussion here, because this is a non-linear relationship. You can see this is a non-linear relationship. It's not a linear relationship. Okay, and therefore we cannot use superposition principle here. 2 is for a fixed beam or fixed column, what will happen? Eccentric load has no effect, should be considered as ideal column. Why is that? Because if your column is fixed, okay, you give a load here, you can convert it into fixed column, the load here, moment here, right? Okay, m0 equal to p into e. In that case, what happens is the moment is completely resisted by the fixed support, and you don't get any effect after that, right? You understand this, that the moment, if you give a moment at the fixed end, doesn't matter, right? Because it will be absorbed by the support itself. It will not even little bit bend more, or slope, there won't be any slope produced there, so it doesn't have any effect. So for a fixed column, it has no effect, so you will consider that as an ideal column. Third is for a cantilever column, use LE equal to 2L in the, we call it second formula, okay? Call it second formula. This is not second formula, this is second formula. All right, but not for any other boundary. For that, you have to find it from first principle. Fourth, and now if I draw the force deformation diagram, theta, and here it is P, right? Not theta, delta. For an Euler buckling load, it was something like this, right? Okay, this was ideal column, E equal to 0. For E equal to some value, it will look like this. This is increasing E. Okay, that's how the curve looks like. So the curve will start from the beginning. For Euler ideal column, it will not start in the beginning, it will just bend because there is a moment acting here. Since there is a moment acting here, it will act like a beam and it will start bending from the instant itself. So if you keep on increasing P, you will see the load going like this. But for an Euler buckling load, there is a sudden failure. But that sudden failure is not seen. Therefore, sudden failure is not observed in eccentric columns. I'll draw one more curve and leave it there. Okay, if you allow me, I'll just draw one more curve. We drew another curve, right? The curve that showed where is your how things behave when you have intermediate column or when you have a long column or short column. So we know that for an Euler buckling load, it looks like this. This is for ideal column. That means E equal to 0. For other values of E, the curve is going to look like this. Sorry. Something like this. And then this. Like this, okay? And it can be like this also. So this is increasing I. Sorry, increasing E. Right. So this zone is your L by R ratio. So this is short column. Here this is long column. Right. And this is your sigma stress. Okay. So as you can see, the eccentricity 0 gives me the limiting boundary for these curves. Right. But as you increase your eccentricity, you get lesser and lesser curves. Right. So, and the effect is more when you have short columns, but when you have long columns, the effects are less. Okay. So with that, I'll stop. And if you have any question, I would be happy to answer. So I will write few things here you have to do probably. One is find max M and find max sigma. These two you do it. Okay. I have also no, there is no mode here. In second formula, there is no mode because the bending starts from the beginning. The modes are only when you have ideal column, not in a non-ideal column. I have shared a book with you. I have shared a book with you. Please look into the columns in that book. That book has a very nice derivation of columns. Yes. So you had some other question, and also look into example 1, 11, 4. So fourth example in 11 in the book. Okay. I'll take a screenshot and send you. Yes. Tell me.
No, sir. I was saying for E tending to 0, sir.
Yeah, E tends to 0. You will have modes. No, it will not go to second mode. It will go to first mode.
No, sir, but in E tends to 0, the maximum thing will become 0, sir. At YLB2 will become 0, right? No, sir, we did this equation, sir. Like Y is maximum at L by2.
Yeah.
So when E tends to 0, this becomes 0, right?
You have to see that. You cannot tell me that way. You have to wait and see. You have to wait and tell me. Check it, check it again.
Okay, sir.
That's why I have given that to you. Had it been so easy, I would have done myself, no? Since it is not that easy, there is a trick there. That's why I gave it to you.
Okay, sir.
See, we do easy things in the class. Okay, difficult things are students to do. That's the benefit of becoming a faculty, right? Okay, so you try it. If you cannot do it, let me know. It is there in the books also. You can just look in the books. They will explain you. With that, I'll stop. I'm
Sir, move a
beyond my
page down for a
Hello?
second. Move a page down for a second.
This part?
Okay, sir.